Hi everyone, I'm Ashin D'Souza and I'm going to be talking about the topic magnetizing field. What is a magnetic field? A magnetic field is a region around a magnetic material or a moving electric charge within which the force of magnetism acts. We use this magnetic field as a tool to describe how the magnetic force is distributed in the space around and within something magnetic in nature. The symbol is denoted by B or H, the unit is Tesla, and the base unit is Newton per second or Coulomb. Illustration of magnetic fields. Magnetic fields can be illustrated by two ways: magnetic field vector and magnetic field lines. Magnetic field vector. The magnetic field can be mathematically described as a vector field. The vector field is a set of many vectors that are drawn on a grid. In this case, each vector points in a direction that a compass would point and has a length dependent on the strength of the magnetic force. Magnetic field lines. Magnetic field lines are a visual tool used to represent magnetic fields. They describe the direction of the magnetic force on the north monopole at any given position.
Hello, my name is Aditya Vadkar and my topic is magnetic moment. Magnetic moment is also defined as the magnetic dipole moment, and its measure has the object tendency to align to the magnetic field. It is represented by a symbol M, and it is given by m dot through L, such that m is equal to the pole strength and 2L is the effective length of the paramagnet. Its SI unit is ampere meter square. It is a vector quantity and its direction is from south to north. It is measured by an instrument called magnetometers. Magnetic pole strength. It is dependent on the nature and the cross-sectional area of a material. It is represented by small m and its SI unit is ampere meter.
Hey guys, I'm Aditya Bhatt and I'll be explaining the slide 11 and 12 on magnetization. So what is meant by magnetization? Magnetization is a vector quantity that is used to measure the density of the permanent or induced dipole moment in a given magnetic material. Thank you.
Hello everyone, I'm going to speak on the topic magnetic susceptibility. Magnetic susceptibility is a dimensionless proportionality constant that indicates the degree of magnetization of material in response to an applied magnetic field. It is caused by the interactions of electrons and nuclei with the externally applied magnetic field. In electromagnetism, magnetic susceptibility is defined as the measure of how much a material is magnetized in a given magnetic field. The ratio of magnetic substance to the magnetizing field is called susceptibility of the medium. And the formula says psi is equal to m upon h, where psi is magnetic susceptibility, m is magnetization, and h is magnetic field strength. Moving to the next slide. Theories of magnetism. The magnetic properties of solids are classified into three categories: Diamagnetism, Paramagnetism, and Ferromagnetism.
Hello everyone, my name is Bhavna Purohit and I'll be talking about magnetic susceptibility of ferromagnetic, paramagnetic and diamagnetic materials. Ferromagnetic materials have a very high and positive value of magnetic susceptibility, and it depends on the applied magnetic field. Diamagnetic materials are materials which align against the magnetic field. Magnetic susceptibility is less than 0, which means it is always a negative value for diamagnetic material. Paramagnetic materials are materials which align with the magnetic field, and the magnetic susceptibility is more than 0, which means it is always a small positive value for paramagnetic materials. Magnetic susceptibility is a dimensionless proportionality constant that indicates the degree of magnetization of a material in response to an applied magnetic field. It is caused by the interactions of electrons and nuclei with the externally applied magnetic field. Thank you.
My name is Blaine Rodriguez and my topic name is magnetic flux. So what is a magnetic flux? It is a measurement of the total magnetic field which passes through a given area. It is useful tool for helping describe the effect of the magnetic force or something occupying a given area. The measurement of the magnetic flux is tied to a particular area chosen.
Hello everyone, my name is Brijesh Desai and I will be explaining about the units and formula of magnetic flux. So the CGS unit of magnetic flux is Maxwell and the SI unit is Weber, which is denoted by WB. So magnetic flux is denoted by phi and magnetic flux formula is given by phi equal to BA cos theta, where phi is the magnetic flux, B is the magnetic field, A is the area, and theta is the angle at which the field lines pass through the given surface area.
My name is Cloyd Rodriguez and I am going to cover the topic magnetic induction or magnetic flux density. The term magnetic flux density refers to the fact that B is magnetic flux per unit surface. This relation is based on Faraday's law of magnetic induction, which states that an EMF is induced in a conductor when magnetic flux through it changes with time. The magnetic flux density or magnetic induction is the number of lines of force passing through a unit area of material B. Magnetic flux density is equal to magnetic flux upon the area, that is, B is equals to phi by A. Unit of magnetic induction is Tesla. The SI unit of measuring the strength of B is Tesla of Weber per meter square and CGS unit of B is Gauss.
Hi, my name is Disha and I'm going to be talking about the difference between magnetic flux and magnetic flux density. Magnetic flux is the measurement of how much the magnetic field lines passes through a given area, while magnetic flux density is the amount of magnetic flux which passes through a unit area placed perpendicular to the direction of magnetic force. Magnetic flux is denoted by phi b or phi. Magnetic flux density is denoted by B. Magnetic flux, the unit is Weber. For magnetic flux density, the unit is Tesla or Weber per meter square. Magnetic flux is a scalar quantity while magnetic flux density is a vector quantity.
So today we are going to talk about the relation between B and H, where B is the magnetic flux density and H is the magnetic field strength, also known as magnetic intensity. The relation between them is B is equal to mu H, where mu is the magnetic permeability.
Hi, I'm Ethan Lorenzo, and today we are going to talk about the relationship between B and H. The ratio B by H in a material is always constant and is equal to the absolute permeability mu of the material. Mu, which is the relative ability of the substance to conduct magnetic lines of force as compared with A, is equal to mu naught into mu r. So therefore, B, which is a magnetic field, is equal to mu naught into mu r into H in any medium, and it is mu naught into H in A where mu r is equal to 1.
Hello, I'm Rishikesh from Group 3 and our topic is Origin of Magnetism, Types of Magnetic Material with Examples. So to begin with, what is magnetization? As you can see, magnetization, also termed as magnetic polarization, is a vector quantity that measures the density of permanent or induced dipole moment in a given magnetic material. So in simple words, you can say that magnetization is magnetic dipole moment per unit volume.
Hello everyone, my name is Ivan Travasos and I will be presenting on the topic, how is magnetization caused? Magnetization is caused by the magnetic properties that arise due to atoms of a solid which act as tiny magnetic dipoles, and they possess magnetic dipole moment. Based on magnetic dipole movement, they are classified into three types: orbital motion of electron, electron spin, and nuclear spin.
I'm Giles Borges. My topic is types of magnetic movements. There are three types. First, orbital motion of electron, electron spin, and nuclear spin. The resulting magnetic moment of an atom is the sum of the orbital and spin magnetic moments of its electrons. Different atomic dipoles may align themselves in different directions to give a net zero magnetic moment. When substance is placed in a magnetic field, the atomic dipoles are aligned in the direction of an external magnetic field. Thus, the material is magnetized.
I am Gemma D'Souza, rule number 16. The topic is types of magnetic material. The magnetic material are divided into three categories on the basis of their behavior in external magnetic field. The first one is a diamagnetic substance. The substances that are weakly magnetized when placed in the magnetic field. However, the magnetization is in the direction opposite to that of the magnetic field. The substances are weakly repelled by magnet. The examples are copper, gold, silicon, water, sodium chloride.
Hi everyone, my name is Gavin Dicona and I will be presenting on paramagnetic substances. Paramagnetic substances are those which develop weak magnetization in a direction of magnetizing field. Such substances are weakly attracted by the magnets. So paramagnetic substances are the substance when taken close to a magnet, it gets weakly attracted by the magnet, means it shows a little bit of attraction. Some of the examples of paramagnetic substances are manganese, aluminium, chromium, platinum, sodium, copper chloride and oxygen.
Hello everyone, my name is Kushi. I am going to cover up ferromagnetic substances. So what are ferromagnetic substances? Ferromagnetic substances are those which develop a strong magnetization in the direction of magnetizing field. They are strongly attracted by magnets. So, some of the properties of ferromagnetic substances are they have a large permanent magnetic dipoles. They can exhibit magnetization even in the absence of external magnetic field. The relative permeability is very much greater than 1. They show a domain structure. So, some of the examples of ferromagnetic substances are iron, cobalt, nickel, gadolinium and alloy like alenico. Thank you.
Hi everyone, I'm Loxley Dias. I'm from the ECS branch, and the topic that I'll be explaining today is the topic that we'll be discussing today is diamagnetism. So the first basic question that arises in our mind is what is diamagnetism and what are its properties? So in simple words, diamagnetism is a property of an object or a material that generates a magnetic field in opposition to the externally applied magnetic field. So basically it is the repulsion of the magnetic field applied to...
Hi, I am the Menezes of FE ECS and I am here to give you a short note on the origin of diamagnetics. In the year 1778, Anton Burpes discovered that when bismuth was kept in an external magnetic field, bismuth got repelled from it. Later, in the year 1845, Michael Faraday named this unusual effect diamagnetism. Michael Faraday stated that diamagnetism was the most weakest form of magnetism in the external magnetic field, and it was usually negligible when other types of magnetisms are there in a field. Michael Faraday conducted experiments and said that diamagnetism is a property of matter, and he concluded saying that all materials are either diamagnetic or paramagnetic in nature. John Tyndall, a natural philosopher, he dedicated his life making research notes and papers on diamagnetics. His work was recognized and he was known in the Royal Society of London.
Diamagnetism is a property of all materials and always make a weak contribution to the material's response to a magnetic field. However, other forms of magnetism such as ferromagnetism or paramagnetism are so much stronger that when multiple different forms of magnetism are present in a material, the diamagnetic contribution is usually negligible. Substances where the diamagnetic behavior is the strongest effects are termed as diamagnetic materials or diamagnets. Diamagnetic materials are those that some people generally think of as non-magnetic and include water and wood. Most organic compounds such as petroleum and some plastics and many metals including copper, particularly the heavy ones with many co-electrons such as mercury, gold and bismuth. The magnetic susceptibility values of various molecular fragments are called as Pascal's constants.
Magnetic materials are independent of temperature, and as they are independent of temperature, they do not obey Curie's law. Curie's law states that the magnetization in a paramagnetic substance is directly proportional to the exerted magnetic field. In short, it is very less as compared to ferromagnetic and paramagnetic substances and is proportional to the magnetizing field. Here, the magnetic susceptibility is also small and negative. The relative permeability is slightly less than unity.
So one of the best example of diamagnetism and is a frog placed in the magnetic field. The basic concept behind a frog being placed in the magnetic field is like there are diamagnetic properties that are present in a living cell. So when a frog is placed in a magnetic field, say suppose a magnetic field of 15 or 20 Teslas, the frog begins to levitate in the air due to the diamagnetic properties of the living cell. So in simple words, like again explaining what is diamagnetism, it is basically the repulsion of the applied magnetic field. So that is the reason when a frog that is placed in a magnetic field, it experiences a force and it levitates in the air. So one of the major subtopic under diamagnetism is diamagnetic susceptibility. So in simple words, explaining what is diamagnetic susceptibility, it indicates whether a material is attracted into or repelled out of the magnetic field. So in a diamagnetic material, basically a diamagnetic material is anti-aligned and is pushed away into regions of low magnetic field due to its property of repulsion to the applied magnetic field. So there are certain questions that I would like to highlight, like say suppose when a diamagnetic material is heated from 300 Kelvin to 650 Kelvin, what is the change in its diamagnetic susceptibility? So the basic answer is there is no change observed when a diamagnetic material is heated from 300 to Kelvin to 650 Kelvin. This is because one of the major properties of a diamagnetic material is that it is independent of temperature. So heating a material will not cause any change to the diamagnetic susceptibility. Another question that comes in our mind is like what causes negative diamagnetic susceptibility? So the answer to it is like there are no total spins in a diamagnetic material since the electrons are closely paired. These materials magnetic field are in opposition to the direction of the applied magnetic field. So therefore lower the negative susceptibility of a diamagnet indicates how much diamagnet a substance or a material is.
Hi, my name is Mayuresh Patil and I am going to start with the subtopic properties of diamagnetic materials. Properties of diamagnetic materials. There are no atomic dipoles in diamagnetic materials because the resultant magnetic moment of each atom is zero due to pair electrons. Diamagnetic materials have no net magnetic moment without the presence of an external applied magnetic field. Diamagnetic materials are repelled by a magnet. The substances are weakly repelled by the field. So in a non-uniform field, these substances have a tendency to move from a strong to a weak part of the external magnetic field. The intensity of the magnetization is very small, negative, and proportional to the magnetizing field. Magnetic susceptibility is small and negative. The relative permeability is slightly less than unity. And further property, we need to know about the Curie's law. The Curie's law states that the magnetization in a paramagnetic material is directly proportional to the applied magnetic field. If the object is heated, the magnetization is viewed to be inversely proportional to the temperature. The law was discovered by the French physicist Pierre Curie.
Diamagnetic materials are independent of a temperature. These materials do not obey Curie's law. A rod of diamagnetic materials comes to rest with its length perpendicular to the direction of the field when it is suspended in the uniform magnetic field because the field is strongest at the poles. A diamagnetic liquid in a U-tube deposits in the limb which is between the poles of the magnet. The magnetic dipole moment is small and opposite to the magnetic field H. If a diamagnetic liquid is placed in a watch glass placed on a two poles pieces that are quite close to each other, then the liquid accumulates at the sides shows depression in the middle where the field is strongest. If the liquid placed on a watch glass placed over two pole pieces that are sufficient apart, then the liquid accumulates in the middle where the field is the weakest.
Hey guys, welcome to group 5. We are going to talk about ferromagnetism and its properties. We are going to cover introduction on what are ferromagnetic materials, what are ferromagnetic, we are going to define it, and we are going to tell the properties of ferromagnetic materials. We are going to also do a differentiation between ferromagnetism and diamagnetism. Let's get started. What are ferromagnetic materials? I am Om from ECS branch. Ferromagnetic materials are materials that tend to get weakly magnetized in the direction of the magnetizing field when placed in a magnetic field. Ferromagnetic materials have a permanent dipole moment or permanent magnetic moment. However, if we remove the applied field, that materials tend to lose their magnetism. What are ferromagnetic materials? Ferromagnetic materials have some unpaired electrons. Due to these unpaired electrons, the net magnetic moment of all electrons in an atom is not added up to zero. Hence, atomic dipole exists in this case. On applying an external magnetic field, the atomic dipole aligns in the direction of the applied external magnetic field. In this way, ferromagnetic materials are freely magnetized in the direction of the magnetizing field. In simple words, we can say that these materials usually experience a weak attraction to magnets. This type of magnetism is known as paramagnetism. It occurs mainly due to the presence of unpaired electrons in the material or due to the partial alignment of randomly oriented atomic dipole along the field.
Hello everyone, my name is Nagesh from the ECS department. So, paramagnetism can be further viewed of two types. In the first type, the magnetic moments are found in the low concentration, which leads to its separation from one another. Their spin do not interact. In the second type, paramagnetism occurs due to the interactions between the magnetic moment. In this case, the interactions are very weak. Therefore, there is no net magnetization when the applied field is zero. Magnetization is based on Schrödinger's law. According to this law, paramagnetic materials magnetic susceptibility X is inversely proportional to their temperature. It is represented as M is equal to X. M is the magnetization and X is the magnetic susceptibility.
Hey, it's me Shams, and I'll try to summarize whatever has been done until now in the form of some figures. So it's been said that paramagnetic materials are materials which have an odd number of electrons in them. For example, gold with atomic number 79, aluminium with atomic number 13. Okay, so what happens in these atoms is that the even number of electrons, that is in gold, for example, we have 79 electrons, the 78 electrons will form a pair. And it'll be one electron that will be left alone, due to which the net magnetic moment of one atom is not zero. It has some net magnetic movement. Okay, but what happens is that when you talk about gold, for example, you just don't talk about one atom, you talk about an entire crystal which has many atoms in it. So what happens is that if you have one atom of gold and the magnetic moment is in this direction, there'll be another atom of gold which will have a magnetic movement in the opposite direction. So it will cancel out each other. That is what's happening over here. So like this atom is getting cancelled by this one is getting cancelled by this one. So the net magnetization of the entire crystal is zero. Okay, but what happens when you apply a magnetic field? When you apply a magnetic field, all these individual dipoles will start to align themselves in the direction of the applied magnetic field, due to which now, as you can see, all are in the same direction. So the net magnetization is not equal to zero. But once you again remove the magnetic field, it will not be aligned in the same direction. It will shift back to what it was before, like this. So like once you have the magnetic field, it's in the same direction, but once the magnetic field is removed, it will again become random, which means it will cancel out each other and the net magnetization will be zero. That's what's said here. If the external field is removed, the atomic dipoles return to the original orientation and magnetization of the entire material becomes zero. Yeah, that's it. Thank you.
Hi, my name is Rahul Vas from the ECS department, and I shall discuss on the properties of paramagnetic materials. The first property of the paramagnetic materials are when the net atomic dipole juncture of a magnetic atom is not nil. Apart from this, the atoms of paramagnetic implications have an endless dipole moment due to them not being paired, deals, or spins. The implications of properties of the paramagnetic materials are feebly enticed by magnetic domains. In the non-invariant exterior magnetic domain, paramagnetic substances transfer from an inadequate field area to a powerful field province. A paramagnetic shaft positions itself similar to the area since the paramagnetic material field is most robust, roughly rods. Apart from this, the next properties of the paramagnetic materials are the paramagnetic liquid in a U-curve ascends to the stem, which is among the rods of the magnet.
My name is Pratik Borkar from FE ECS. Properties of paramagnetic material. The vigor of magnetization is extremely diminutive, obstinatic, and instantly proportionate to magnetizing domain. The magnetic exposure is miniature and obstinatic. The comparable permeability is negligible and more significant than 1. Moreover, the field inside the material is more significant than the magnetizing area. Another property of paramagnetic material is that the magnetic field sequence evolve more idiotic inside paramagnetic substances. Magnetization of paramagnetic implication is immensely inverse and it is symmetrical to conclusive temperature. Moreover, paramagnetic substances follow the rule of Curie's law, as per which magnetic exposure is inversely commensurate to decisive temperature. In the end, the last one of the property of paramagnetic material is that it is when paramagnetic dipole moment point of a paramagnetic implication is smallish and similar to magnetizing domain of field.
Hi, my name is Miles Rodriguez from the ECS department, and I will be discussing the difference between paramagnetic substances and diamagnetic substances. In paramagnetic substances, the substances are weakly attracted by the external magnetic field, whereas in diamagnetic substances, there is slight repulsion by the external magnetic field. In paramagnetic substances, these substances become diamagnetic under high temperature, whereas in diamagnetic substances, the temperature has no effect on the substances. Paramagnetic substances have relative permeability lesser than 1, and in diamagnetic substances, the permeability is greater than 1. In paramagnetic substances, their magnetic susceptibility is positive, and in diamagnetic substances, their magnetic susceptibility is negative. Paramagnetic substances contain unpaired electrons, whereas diamagnetic substances contain paired electrons. Paramagnetic substances do not show any leviation, whereas diamagnetic substances show static magnetic leviation.
What is ferromagnetism? Ferromagnetism is the basic mechanism by which certain materials such as iron form permanent magnets and are attached to magnets. Ferromagnetism is seen in elements having particularly 3D shells such as iron and gallium. The cause of this type of magnetism is due to alignment of patterns of atoms when an external magnetic field is applied. Let's look at some of the properties of ferromagnetism. The first property is that the magnetic field lines tend to crowd into ferromagnetic substances. If I were to put this in simple words, I would say that the distance between the magnetic lines in the ferromagnetic substance is less as compared to the distance between these lines in the external region.
Hello everyone, my name is Reeve Rodriguez from FE ECS. I'm part of Group 6 and we will be covering the topic ferromagnetism and its properties. Today I'm going to be covering the second and eighth property. So the second property of ferromagnetism is when a ferromagnetic substance is placed in a non-uniform magnetic field, it moves from a region of weak field to a region of strong field. So this basically means when a ferromagnet is placed in a magnetic field, it gets strongly magnetized and moves from a region of weak field to a region of strong field.
Hello everyone, I am Ruban Wallis from FE ECS from Group 6 and we will be covering the topic ferromagnetism and its properties. Now I will be covering the third and the ninth property. So the third property of ferromagnetism is when a paramagnetic rod is suspended freely in a uniform magnetic field, it aligns itself in a direction parallel to the field very quickly.
I'm Ria and I'm from ECS and the name of my topic is susceptibility of ferromagnetic materials has a larger value greater than 1. The susceptibility is the ratio of magnetization to the ratio of magnetic field intensity H. The ferromagnetic materials when placed in an external magnetic field get strongly magnetized. The formula for susceptibility is given by Xm is equal to m upon h, where m is the magnetization and h is the magnetic field intensity. This implies that the ferromagnetic materials have a larger value greater than 1.
My name is Ridhima Varnikar and I'm going to be explaining you the properties of ferromagnetic substances. The fifth property of ferromagnetic substances states that the magnetic permeability that is nu is very large for ferromagnetic substances. This is mainly because they have a high susceptibility positive value to the external magnetic field.
So the sixth point, relative permeability is an order of 1000. So basically relative permeability is defined as the ratio of material permeability to the permeability of free space. It's also denoted as mu r, where mu r is equal to mu upon mu m, and mu r is always greater than 1000.
The next property we'll be looking at is susceptibility decreases with temperature and change in paramagnetic substances. It basically follows the Kerr temperature. What is the Kerr temperature? It is the temperature at which certain magnetic materials undergo a sharp change in their magnetic properties, as seen in the graph.
And the eighth property of a ferromagnetic substance is is that these substances have permanent dipole moment. And this basically means that ferromagnetic substances retain a dipole moment even after removal of the magnetic field, and so they do not lose their magnetism after the external field is removed. Thank you.
And the ninth property of ferromagnetic substance is M changes non-linearly with age, thus attains saturation level ultimately, where M is the magnetization of material and H is the external magnetic.
B vector shows hysteresis. If we take the magnetic field intensity H on the x-axis and the magnetic field B on the y-axis and increase the magnetic field intensity, at a point the magnetic field intensity H will stop increasing, but the magnetic field B will become constant. If we now decrease the value of magnetic field intensity to 0, the magnetic field B will not completely decrease but have some value on the y-axis. If we still further continue to decrease the magnetic field intensity, the magnetic field intensity H at a point will stop decreasing and the value of the magnetic field B will become constant. This curve so formed shows hysteresis, which means that ferromagnetic materials show hysteresis.
The 11th property states that the magnetization persists even after removing the magnetic field. This is because they exhibit a strong attraction to the magnetic field and hence they can retain their magnetic properties even after the field is removed.
So the 12th and the last point is no liquid is ferromagnetic. This is mainly because in liquids and gases they possess weak attraction as the ferromagnetic substance become permanently magnet. So ferromagnetism is not found in liquid and gases. And also ferromagnetic substances have high susceptibility to magnetization. Therefore, liquid and gases aren't prone to be magnetized.
Hello everyone, so we are going to explain you the domain theory of magnetism. It was given by West in 1907. It states that a magnetic material consists of small regions called domains. Each domain consists of magnetized atoms whose magnetic moments are aligned in the same direction. That is, magnetization is in the same direction. For example, in the first picture, individual domains have the atoms aligned in the same direction. Same goes to the second picture, which is a one single whole different domain in which their individual magnetic moments of the atoms are aligned in the same direction.
The magnetic moments of different domains are in different directions. The magnetic moments of different domains cancel out each other and the net magnetization of the material remains zero.
When a magnetic field is applied to this ferromagnetic material, it gets magnetized due to two mechanisms, which is domain growth and domain rotation.
Hi everyone, my name is Ruza Sawant, roll number 38, and now I will be explaining one of the aspects how a ferromagnetic material is magnetized, that is, domain growth. Applying a magnetic field to a ferromagnetic material causes the domains that are parallel to the magnetic field to increase in size, while the domains that are anti-parallel or not parallel to the field decrease in size or shrink. In this way, ferromagnetic material gets magnetized. Thank you.
Assuming I have an iron bar and I apply a strong magnetic field to this iron bar, the domains within this iron bar will rotate with respect to the magnetic field applied to this iron bar. This way, the ferromagnetic material gets magnetized.
When we remove the field, the domains stay aligned, and we now have a new magnet. While these magnets are not truly permanent, some magnet domains will not return to their original state for much longer than a single lifetime.
Hello everyone, my name is Soumya Maujekar and the topic I am going to cover is hysteresis loop. To start with, hysteresis loop shows the relation between the magnetic flux density and the magnetizing field strength. Loop is generated by measuring the magnetic flux coming out from a ferromagnetic substance while changing the external magnetizing field. It is also referred as the BH loop. From the hysteresis loop, we can determine a number of properties about a material such as retentivity, residual magnetism, coercive forces, permeability, and the reluctance. As can be seen from the picture, that as we follow the ladder from A through G, we generate important magnetic data about a material that help us understand material's magnetic properties. Magnetic flux density will increase from point A in presence of the applied magnetic field until it reaches maximum, where it is no longer responding to the increase in magnetizing field, which is at point B. This point is called as positive saturation.
The next thing we do is go back to the left along the horizontal axis towards the origin. Pushing to the left on the magnetic axis, we continue to increase the magnetic field in the opposite direction until reaching the point E, which is the point of negative saturation. The point is just like point B but just in the opposite direction. The shape of the BH curve in hard and soft magnetic materials. In soft magnetic materials, they have a thin hysteresis curve, so they see a lot of usage in applications that require them to switch polarity often, such as in transformers and motor windings. Whereas in hard magnetic materials, they have a wide hysteresis curve, which makes them practical in applications where they need to exert their magnetic field on soft magnetic materials. Soft magnetic materials have a lower reminiscence and lose a large percentage of their magnetic field by the time they cross the zero line. They also have a steep negative slope of demagnetization at the zero line, whereas in hard magnetic materials they have high remanence and have lost only a small percentage of their magnetic field by the time they cross the zero line. Their slope is demagnetized at the zero line, is very shallow and does not steepen until it goes too far to the left of the zero line.
Hello everyone, I'm Sean DeCosta. I'm from FE ECS and I'll be talking about retentivity. First, let us know what happens during the hysteresis effect. When a ferromagnetic material is magnetized by applying the external magnetizing field H, after magnetization, even if we remove the magnetic field, the material will not relax back to its zero magnetization position. Now let's see what is retentivity. It is the amount of magnetization present in a ferromagnetic substance even after the magnetic field is removed. It is the material's ability to retain a certain amount of magnetic property when an external magnetizing field is removed. That's what I said previously. The value of B at the point Y on the hysteresis loop is retentivity. The units in which retentivity of a material is measured is Weber per square meter or Weber raised to minus 2. Now let's see what is coercivity.
Hello everybody, I'm Shian and I'll be presenting on coercivity. Coercivity is the measurement of a ferromagnetic substance's ability to withstand an external magnetic field without getting demagnetized. Here the value of H in the hysteresis loop is the coercivity. The units of coercivity is measured in ampere per meter. It's also known as cohesive force or cohesive field. Well, coercivity and retentivity is what Sean did earlier, are dependent on the type of magnetic, type of material we are using. Preferably, this is supposed to be ferromagnetic material. We are using and the conductivity of the magnetic field in that particular material. Again, this is supposed to be ferromagnetic. Thank you.
Hello everyone. Now I am going to tell you about hysteresis loss. So basically saying hysteresis loss refers to nothing more than a loss of energy in a form of heat in the presence of magnetic hysteresis, or we can say due to the presence of magnetic hysteresis a fraction of power. A fraction of power is lost in a form of heat. The portion of power lost corresponds to the difference between the energy stored and the energy returned back to the magnetic core, and this resultant is called hysteresis losses. Now let us see some other definitions of hysteresis losses. For firstly saying, if a magnetic field applied to a magnetic material is increased and decreased back to its original value, the magnetic field inside the material does not returns to its original value, or the value it was at the start or at the beginning before increasing the magnetic field on it. Or we can say, when the internal field lags behind the external field, this behavior results in the loss of energy, and this loss of energy is called hysteresis losses. When a sample is continuously magnetized and demagnetized, there is a loss.
So, I'm Shaunak and I'll be talking about hysteresis loss. So the factors affecting the hysteresis loss are the frequency of magnetization, the volume of the material, the area enclosed by the hysteresis loop, and the area of the hysteresis loss, which is directly proportional to the area under the hysteresis loop. For the loss materials, the hysteresis loop is narrow. Now moving on to magnetic hysteresis loop for soft and hard materials, as you can see from the picture, the soft ferromagnetic materials has a small coercive force, while the large ferromagnetic material, for the hard ferromagnetic materials have a large coercive force. The area and the shape of the magnetic material are an important parameter which decide the suitability of a material for a particular application. In the hysteresis loop of soft ferromagnetic material, all the values such as residual magnetism and coercive force are moderate. Hence, these materials are used for making electromagnets. In the hysteresis loop of hard ferromagnetism, all the values such as the residual magnetic coercive force and coercive force are large. Hence, this material is used for making permanent magnets. Thank
Hello, I'm Shreya from FE ECS and I'm here to tell about the examples of soft magnetic materials. As said by Shravani, soft magnetic materials are those materials which have smaller area enclosed by their hysteresis loop, low remnant magnetization, low coercivity, and high permeability. The best examples of soft magnets are iron silicon alloys, nickel iron alloy, and iron. Iron silicon alloys are generally used in applications requiring higher electrical resistivity, higher permeability, and lower corrosive force and residual magnetism than provided by either carbon steels or soft magnetic stainless steels. The commonest soft magnetic materials are soft iron, nickel iron alloys, and soft ferrites. Soft magnetic materials are used for the construction of cores for electrical machines, transformers, electromagnets, etc. As an important soft magnetic material, pure iron has high permeability and saturation magnetization. However, it will produce huge core loss during use and the permeability will drop drastically with increasing frequency.
Hello everyone, I am Shravani Dhere from FE ECS. Today I am here to give an introduction on soft magnetic materials. What are soft magnetic materials? Soft magnetic materials are those materials that can be easily magnetized or demagnetized. Magnetized in sense they become magnet itself, and demagnetized they lose their magnetism. They are said to be soft magnetized because magnetic field in soft magnetic material can be reversed, so they are said to be magnetically soft. They typically have intrinsic coercivity less than 1000 ampere meter inverse. Now, what is coercivity? The magnetizing field needed to demagnetize the magnetic material is called coercivity. The main parameter often used as a figure of merit of soft magnetic material is their relative permeability, that is equal to magnetic field density upon permeability in vacuum into intensity, which is a measure of how readily the material responds to applied magnetic field. The other main parameters include coercivity, saturation, magnetization, and electric conductivity. Properties of soft magnetic material are low coercivity, high permeability, and it produces very narrow hysteresis loop. Examples include alloy of iron silicon and alloy of iron nickel.
Hello everyone, my name is Parsh Alve. Basically, I'll be covering three properties of soft magnetic materials. Now to understand this, your concepts of hysteresis must be clear. Moving on to property number 1, soft magnetic materials have low hysteresis loss due to small hysteresis loop area. Look at the first topmost image. We can see a hysteresis loop having a small loop area. And from the concepts of hysteresis, we know that hysteresis loss is equal to the area of BH curve. So lesser the area of loop, lower is the hysteresis loss. Moving on to a simple property, that is property number 2, these materials can be easily magnetized and demagnetized. Property number 3 says that the coercivity and retentivity are small. Now again, from hysteresis concepts, we know that retentivity is the magnetic flux density remaining in the material when applied field is made zero. Look at second figure. In simple words, in the figure, CA is the retentivity. Also again, referring to concepts in hysteresis, we know that the value of applied field required to make the magnetic induction within the material zero is called coercivity. So again, look at the second figure. In simple words, to understand it, AD is the coercivity. Now, based on the definition of coercivity and retentivity, look at the figure 1. It is evident that the coercivity and retentivity for soft magnetic materials, it is very small.
Hello everyone, my name is Tabreza Khasnali and I'm going to further talk about soft magnetic materials. Now, soft magnetic materials have high value of permeability and susceptibility. Now, high permeability means when a soft magnetic material is used as a core, it will allow huge amount of magnetic flux lines to pass through it. Now, some examples are iron silicon alloy and nickel iron alloy. Soft magnetic materials have very high resistivity, hence low eddy current loss. The given pictures are of iron silicon alloy and nickel iron alloy. Now let us talk about hysteresis loop of soft magnetic materials. The points to note here are soft magnetic materials have low value of coercivity, and also soft magnetic materials are easy to magnetize or demagnetize. The given hysteresis loops are of soft magnetic material and hard magnetic materials. Now in soft magnetic materials, we can see that a small increase in external magnetic field leads to easy magnetization of soft magnetic materials. And to demagnetize the soft magnetic material, only a small amount of reverse magnetic field is required, which is also known as the coercive force. Thank you.
Hi, I'm Tanish Lotlikar and I'm here to further speak about soft magnetic materials. So I'm going to speak about applications of soft magnetic materials. One of the applications are preparations of magnetic core material used in a transformer. So in most types of transformer construction, the central iron core is constructed from a highly permeable material, commonly made from the silicon steel laminations. These thin laminations are assembled together to provide the required magnetic part within the minimum of magnetic losses. Here is the diagram given. So the minimum for the minimum magnetic loss, soft magnetic materials are used. Thank you.
I'm Troy Fernandez from FE ECS. Applications of soft magnetic materials. Magnetic materials are materials which can be easily magnetized and demagnetized. And use of soft magnetic material in an electric motor. An electric motor is an electric machine that converts electric energy into mechanical energy. Most electric motors operate through the interaction between motor's magnetic field and electric current in a wire winding to generate force in the form of torque applied on the motor's shaft. Soft magnetic materials play an important role in an electric motor, where they enhance the field produced by an electric motor.
Hi, my name is Vanshika.
and I'm from Group 10. Our topic here is hard magnetic materials, examples and its applications. So I'm going to explain what exactly hard magnetic materials are. So hard magnetic materials are the materials that are difficult to magnetize or demagnetize once they become powerful long-lasting magnets. Also, their retentivity and coercive force are high in hard magnetic materials as compared to the soft magnetic materials. So, what exactly is retentivity? It's a magnetic flux density remaining in the material when the applied field is made zero. So, that's retentivity. And coercive force is a value of applied field required to make the magnetic induction within the material zero. So, that's coercive force. So, retentivity and coercive force both are high in hard magnetic materials as compared to the soft. As we can see in this picture, hard magnetic materials, there's a large coercive force, and in soft magnetic materials, there's a smaller area and smaller coercive force. Coming to the third point, area of hysteresis loop is large and hence hysteresis loss is large. So what exactly is hysteresis loss? So when a ferromagnetic material is made to pass through a cycle of magnetization, there's an energy that is spent which comes out through heat. So that's hysteresis loss. So when the hysteresis loop is large, the hysteresis loss is also large, and the region beneath the hysteresis loop is nearly rectangular and stands fairly tall. So that's hard magnetic material and its properties. Thank you.
Hi, my name is Viraj Parab and I am from FE ECS. Today I am going to tell you about properties of hard magnetic materials. As you can see, this is the BH curve. On the left hand side you can see it's for soft ferromagnetic materials, and the right hand side is for hard ferromagnetic materials. The major differentiation between them is the coercive force. On right hand side you can see the graph for the initial permeability. The initial permeability of hard magnetic material is very low. So this is a permanent magnet, and the major difference between the permanent magnet and a temporary magnet is permanent magnets retain magnetic properties over a long period of time, and temporary magnets retain only for a short period of time when they are present in a magnetic field. This is a picture of a neodymium magnet, and this is a picture of a nickel coated magnet.
Cobalt is one of the naturally occurring ferromagnetic metals, iron and nickel being the other two with a very high Curie temperature owing to the strong exchange interaction among the 3D electrons, a paradigm of developments for hard and semi-hard magnetic materials based on cobalt. Partially occupied 3D orbitals and high magnetic moment make cobalt an important constituent of the major ferromagnetic materials. As a metal, it can be crystallized in HCP, FCC, or E-cobalt structures. Cobalt has been used in many industrial, commercial, and material applications. Below are some of its common applications. Cobalt is used widely as one of the metals needed to create hard, permanent magnets with high coercivity, such as aluminum nickel cobalt Alnico alloy series. Alnico magnets are used in motors, hard disk drives, and sensors. Magnetic resonance imaging is an example of an application for these magnetic alloys. Hard metals, in which cobalt is used as binding material, consume roughly 12% of total cobalt. These include cemented carbides and diamond tools that are used in cutting applications and mining tools. Cobalt is also used to produce permanent magnets such as previously mentioned Alnico and Samarian cobalt magnets. Magnets account for 7% of cobalt metal demand and are used in magnetic recording media, electric motors, as well as generators.
Hello, myself Yash Sullakar, and I am going to explain you about the examples of hard materials. So first of all, we learn about what are hard magnetic materials. So the hard magnetic materials are also known as the permanent magnets. They are the magnetic materials that can retain their magnetism. The initial permeability of hard magnetic materials is modest and they have a higher hysteresis loop. Therefore, hard magnetic materials are those which can get permanently magnetized. Example iron, nickel, neodymium, etc. So, let's learn in detail about what is neodymium magnet. A neodymium magnet, also known as the NIP or neo magnet, is the most widely used type of rare earth magnet. It is a permanent magnet made from the alloy of neodymium, iron, and boron to form the Nd2Fe 14b tetragonal crystalline structure. Neodymium magnets are the strongest type of permanent magnets available commercially. This magnet is anti-ferromagnetic but only at temperature of below 19 Kelvin. The neodymium atom can have a large magnetic dipole moment because it has 4 unpaired electrons in its electron structure. Neodymium magnets have higher eminence, much higher coercivity and energy product. These magnets are used in loudspeakers, headphones, locks of doors, mechanical e-cigarette firing switches, and electric motors. These are some pictures of neodymium magnets.
Hello guys, this is Utkasha Thakur from FE ECS and I'll be presenting y'all on application of hard magnetic materials. Hard magnetic materials are also known as permanent magnets. There are various types of application on it, in which you can say automotive, as in where you use hard magnets as motor drives for fans, wipers, injection pumps, starter motors, controls for seats and windows, etc. In telecommunication, you use hard magnet in microphones, loudspeakers, telephone ringers, etc. In data processing, you use them in printers, stepping motors, disk drives, and actuators. In consumer electronics, you use them in home computers, clocks, DC motors for showers, etc. And in electronics and instrumentation, you use them in energy meter discs, sensors, dampers.
Hi, I'm Vihan Naik Karmali from FE ECS, and I'll be talking about the applications of hard magnetic materials today. So, to begin with, the magnetic hard materials are used for industrial purposes like lifting apparatus and robotic systems, meters, etc. In addition, they also used in astro and aerospace technologies like autocompass, which is used for navigation, and its needle is made up of a permanent magnet. The magnetic couplings works by using the power generated by a permanent magnet also. Mm, Furthermore, they are used for biosurgical methods like MRI body scanner. So, a MRI body scanner is basically a large tube which contains superconducting hard magnetic materials. Wound closures. So, magnets also help in healing wounds through magnetic static field therapy. So, now let's get a quick recap of whatever we have done so far. So, what are hard magnetic materials? So they are basically magnetic materials which can retain their magnetism, and because of this property, they are also referred as permanent magnets. So these are some of the examples of hard magnetic materials, which includes ions, which is the most common example. Then comes the alnico magnets, which contains aluminium, nickel, and cobalt. And the strongest of these is the neodymium magnets. So these are some of the applications of hard magnetic materials. They are used for automotive purposes in telecommunication, data processing, consumer electronics, electronics and instrumentation. They are also used for industrial purposes, astro and aerospace technologies, and biosurgical methods. So yeah, this was all we had on this topic. Thank you.